worry.
All right.
How I can just keep on doing it.
Oh, I know.
Here we go.
But like,
Today we're going to talk about the average rate of change. So notes 1.2, everybody ready? The average rate of change is simply the slope through these 2 points. Look at the average rate of change formula in the box there. Have you ever seen that before? That's slope, ain't it? The average rate of change is slope. We're talking about how does y change with respect to x. That's slope. So, find y values for the function, and then find the slope between those 2 points. That's what we're going to do. So, find the y values and then find the slope. So here we go with example 1. Your function is this, and your interval is this. The rate of change, the average rate of change, is going to be f of -1 minus f of -2 over -1 minus -2. What does this mean? This looks different, but this is the way we have to write it. But what's this? That's just y. That's y2, right? So we're just going to find y2, we're going to find y1, we're going to subtract them, and then we're going to take x2 minus x1. And that's your average rate of change. This is the way you have to write it though, guys, with the function notation. It means the same as slope. It's y minus y over x minus x, but write it this way. All right, so what's f of -1? Watch it. This is going to be +1, isn't it?
Yeah.
And then that'll be -3.
Yeah.
So that's going to be -2. F of -1. Plugging it in here.
Yep.
And then I need f of -2. What's that going to be? 8 minus 6?
Yep.
2. And then I'm dividing by basically this. So it looks like my rate of change is -4, my average rate of change. That okay? So what about B? Same thing. What's our average rate of change going to be? H of 4 minus H of 1 over 4 minus 1. Is that all right? Here we are just in lesson 1.2. That was on the AP exam, a rate of change problem. Harder than this, but the idea. This is how you have to write it. Okay, what's H of 4 for this function? What? I heard somebody ask a question. Does someone have a question? No? Alright, so what do you get if you put in 4? 5 over 10. So 1/2. What do you get when you put in 1? 2 over 7, that's lovely. Over 3. Alright, we're going to get a little arithmetic practice here. What do you want to do with that?
Never mind. I don't think I'm right.
Say it anyway, what
usually
that
wrong.
doesn't matter.
I was gonna say get a common denominator on the top.
Nothing wrong with that. Nothing wrong with that.
Let's do it.
So this is called a complex fraction. It is little fractions inside of a big fraction. The most efficient, I'm not saying the only way, the most efficient way of taking care of it is to multiply each part of the problem by that common denominator that Enzo was going to find. So I'm not going to necessarily get a common denominator. I'm going to figure out what the common denominator would be and then multiply everything. What's the benefit of that? Well, what happens to this fraction? It becomes 7. And what happens to this fraction? 4. And then the denominator is 42. So I end up with 3 over 42, which I think actually reduces to 1/14. So your average rate of change is 1/14. Now, try example 2. You are going to do exactly the same thing, but you're doing it from graph. So go ahead, find your average rate of change, you and your partner. Set it up correctly. So set it up with function notation. So it'll be g of 3 minus g of -1 over 3 minus -1. So that's going to be your setup. Then use your graph to find your y values. Can you interpret the graph? What's g of 3? 4. What's g of -1? 0. Did you get 1? So your average rate of change is 1. All right, look at table 3. Same thing, only this time you have a table of values. So we did it, the first 2 were with equations, then you did it with a picture, now you're doing it with a table of values. So it'll be your average rate of change will be A of 2,000 minus A of 1850 over 2,000 minus 1850. That has to be shown right there. Get in the habit of showing that. What's A of 2,000? 81.83. What's A of 1850? 46.10. And it's 150. Might need a calculator here. Did you get 0.2382? Did anyone get that? Okay. Now, include unit of measure.
Years?
So what is that 0.2382 represent?
Age, growth per year.
Okay, well, that would be a good way to say it. Added years of age per year of past time. So in other words, every year that goes on, you can expect to live 0.2382 years longer. So this is kind of awkward, but we can't say years per year, that doesn't make any sense. So this is how much we're gonna add on to our average age,
So like,
life expectancy, every year that passes.
so like every year the life expectancy goes up 23%.
Increases by that much, yep, the life expectancy is increasing. By almost a quarter of a year.
Is that true? I think this is true.
I'm not an expert on this. I think it was true for a long time, but I think recently
I'll probably start going back
it's
down.
not going
Yeah. That checks out.
Can we find an instantaneous rate of change? Okay, everything we've done so far has been an average, because we have had two values, right?
Yeah.
Could we find a rate of change at an instant? Not at between 1 and 2 seconds or 1 and 2 years, but at 1.5 years. Could we find the actual rate of change at that instant? And the answer is yes, we can, using calculus. That's a calculus exercise. How can we do it in this class? Well, look at example 4. We're not gonna be perfect, because we're not gonna use the first derivative to do this. But let's look at what our strategy is gonna be. You got a ball thrown in the air, there's your projectile motion. By the way, that's the projectile motion formula for meters. The one we used was feet. This is meters, that's why there's a 4.9 there. Find the average change in the height of the ball over the following intervals. Now, look at the intervals, guys. What's happening? The first one, how wide was the interval? 0.1. The second one, the interval was 0.01, and then it went 0.001. So do you see what we're doing? We're gonna zero in and get as close as we can and be able to approximate the rate of change at 1. Okay, because we're getting closer to it. All right, so your row is gonna do A. You're gonna find your average rate of change on that interval. You guys are gonna do B, you guys are gonna do C, and I'm gonna do D. So find your average rate of change, set your formula up correctly. So mine will be h of 1 minus h of 0.999 over 1 minus 0.999. That's going to be my average rate of change. Make sure you're setting yours up the same way, using this function. Fred, you guys got an answer over there? What did you come up with?
14.71.
14.71?
Yep.
Okay, did it come out that way exactly, or is there more?
Yeah, exactly.
Okay. Did you guys get B? 15.15, exactly. The reason I keep acting exactly is how are we supposed to round?
To the 1,000.
At least 1,000, right? At least 1,000. But if it comes out like that, it comes out like that. What'd you guys get?
15.1951.
1951. And I got that right there. Might have been a mistake. Would somebody double check mine? Did anybody else get this right here? I'm just wondering. That's not what I expected to happen, so I'm just wondering. Okay, well, based on that, can you approximate what you think is the average rate of change at 1 second? Oh, well, now here's the problem. I understand what you're saying, but here's the problem. This one was over an interval that's 1/10 long. This one is over an interval that's inside that interval, but it's 100 wide. This one's inside that one, but it is 1,000th wide. What about these two? Mine was 0.999 to 1, and this one was 1 to 1 to 1.001. Is that right? Am I right?
Yeah,
Am I
yeah,
right?
yeah.
Okay. So, what about these two now?
He's just before C.
So here's 1, the number 1. Here is that value, and here is this value. Could I maybe average those two? And looking at the numbers, I mean, what is the average of those two? I'm thinking 15.2. Because this one is what, 49 10,000ths below 15.2? And this one is 49 10,000ths above 15.2? So I think our actual instantaneous rate of change is 15.2 meters per second. Rate of change, meters per second. Does that make sense to you? That it would be legit to average these two, but not these over here? This is apples to apples.
So then, our A and B just kind of like showing us where
Yeah,
the
where
point
we're
should
heading,
be.
what's going on.
So we shouldn't really have to do it.
We
It's
would
just kind
never
of
have done that. So if somebody said to me, using this procedure, find the instantaneous rate of change at 2, I would do 1.999 and 2.001 and
Okay.
see what's going on with those two.
Wait, so like that interval or 1.99 and 2?
1.99 to 1,
Okay.
and then, or not to 1, to 2, and then 2 to
Got it.
2.01, yeah. Okay? All right, the rate of change of a function at a particular point is the rate that the y values change if the x values change. This is instantaneous rate of change. We can't find the rate of change at a particular point. We can do the following two things. We can estimate the rate of change at a point by finding the average rate of change over a very small interval. Or we can also estimate rates of change at two different points by estimating individual rates of change using the concept of a tangent line. So what that means is, that was a little more confusing. The first one is what we did. This one is a little bit more confusing. So we've got, that would be a parabola opening down, right? And we want to know the rate of change at this point right here. Could we find the slope of this line? Yeah, we're using 2 points on that equation, right? We could do that. That is not a tangent line. That is what we call a secant line. But what happens when I move that point closer? Now it's still a secant line, but the closer I move those 2 points together, do you see the closer the line becomes a tangent? If those 2 points get really close together, then it's a tangent line. And that is the instantaneous rate of change. It's the slope of the tangent line. So you just want to move those 2 points so close together that they're almost a tangent. That's what that means. All right, we already talked about all that. All right, example 5. For each scenario below, determine whether the two quantities have a positive rate of change or a negative rate of change. Rate of change is slope. Are the two quantities related the same way? Let's take a look at it. A child's age versus the child's height. Would you say that would be positive or negative?
Positive.
Positive, because under normal circumstances, the older the kid gets, the taller he gets, right? A golfer's skill level versus his score. Negative, because the higher that his skill level goes, the lower his score goes, theoretically, right? The height from the ground of a coin dropped, I guess that's a building, I'm not sure, versus the speed of the coin as it falls. So, the coin is coming down.
Positive. The accelerator.
Okay, let's think about it. The coin is coming down. What is happening to its height?
It's going down.
It's going down. What's happening to its speed?
Increasing.
It's increasing. So that would be a negative slope. That would be a negative slope. One is going up and the other one is going down. Negative slope. Alright, the graph of F is shown along with the line tangent to F at x equals -4. In calculus, we talked about this, we will learn that the slope of the line tangent is the true rate of change of F at that point. In other words, the slope of the tangent line is the instantaneous rate of change. Estimate the rate of change of F at x equals -4 using the slope of the line tangent to F at x equals -4. All right, we're estimating. Can we find 2 points on that line so we can find the slope of it? Can you name 2 points on that line? -2.5 looks like 1 for sure. How about -5.1? Is that kind of close? All right, give me tell me what you want me to do then. Yeah, you don't like my idea, let's come up with another one.
Come on, dude.
-5.95.
All right,
There it goes.
so here we go, find the slope. We're finding the slope of that line. So 0.95 minus 5 over -5 minus -5. I don't know about my arithmetic, I think it's right. Did you get 1.35? Now on your graph, is that okay with everybody? Did I do my math right? Now on your graph, sketch lines tangent to F at those 5 black points. Actually, there's only 4 on the graph, I think, he's already drawn one. So draw your tangent lines. As best you can. And then decide, do we have, oh, there are 5. Do we have, a greater rate of change at 4 or 5? X equals 4 or X equals 5. Now remember, rate of change is slope. Rate of change is slope. So if you draw your tangent lines at 4 and at 5, which one looks to have a bigger slope? The one at 5, because the line is steeper. That's example 8. The graph of F has a greater rate of change at 5 because the tangent line is steeper. All right, here we go. Our favorite stuff. The rate of change is positive, the graph is increasing. The rate of change is negative, the graph is decreasing. The rate of change is increasing, the graph is concave up. The rate of change is decreasing, the graph is concave down. Okay, we've already talked about all those things. Keeps coming up because it's so important and it gets so confusing if we're not careful. So look at example 9. What does that look like, by the way? Looks like a square root that's been moved up and over. All right, so the graph of F is, would you say increasing or decreasing? Increasing. Is it going up? And concave down. Down. That thing's not going to hold any water. That's concave down. Because the rate of change of F is positive. Rate of change is slope. Slope is positive. And the rate of change of F is decreasing because we are concave down.
But for this, the slope will never get 0 or below, right?
What now? Say what?
Like the slope of this line will never get below 0.
Right. Right. So that would be what we call an increasing function. It's increasing on the All right, example 10, you and your partner circle the right answers. F, G, and H. You and your partner.
Let's go, right?
Circle the right answers for the graphs of F and G and H.
Like over time. Okay.
Yeah, it's not good.
Wait.
How's that a positive feature?
These concepts are so simple, but they get all jumbled up.
Yeah, there's too many great changes. Yeah.
I'm like,
Oh, yeah. The video's so
What?
Okay, wait, so, on page
you have to look at if it's more water or not.
I don't know. It's on the.
I will. That's boring. Okay, now this one knows. Now this one.
All right, let's look at F. Everybody should have gotten F done. Let's look at F.
What do you have to say about this? How do you feel about the purple? Yeah, we're gonna do that. No, dude, it is.
Okay. Number 11, the graph in F. The graph of F is, what did you say? Well, the graph of F is positive.
What's going down?
Okay, so we gotta separate some stuff here, folks. What is negative? The slope is negative. But the graph itself is positive. Look at those y values, you guys. Look at the y values. Where are they? Above the x-axis. The curve is positive there. So when we talk about a graph, the graph being positive or negative, here is where the graph is positive. Here is where the graph is negative. We're talking about the actual graph. Okay, we're not talking about slope and all that. We're talking about the actual points themselves. So your y values, f is a function, y values are positive. All of your y values are positive. That's a positive graph.
Just with the line.
Yep. Nope. Nope. Positive, above or below. Yep. Now, what did you say about underneath that? The graph of f is,
I said
I hope you said, what's happening to this graph, you guys, as you draw it? What's happening?
decreasing.
It's decreasing. talking about how the rate of change is changing. So some of you may have looked at that and say, hey, it's concave up. Okay, that's not what this question says. It says F is the graph of F. How is it, what's it doing? It's going down. That is decreasing. That is a positive decreasing function.
Why does it say if it's positive?
That's rate of change.
Yeah, we're not talking about the rate of change. We're talking about the graph itself, Gus. Okay? So now that's in the second column. The rate of change of F is, the rate of change is the slope. The slope of F is negative. The rate of change of F is increasing or decreasing? Increasing because that thing is concave up. So, but there are 4 questions asked in this little thing here. The first 2 on top of each other deal with the graph itself, the function itself. It's positive and decreasing. The other 2 deal with the slope, the rate of change. The rate of change is negative and increasing, becoming less negative because it's concave up. All right, let's try G. How do we do with G? The graph is negative, absolutely negative, and increasing or decreasing? Increasing, very good. This picture, the graph, is all negative and it is increasing. Now, what about its rate of change? The rate of change of this is positive, slope, positive, going up, and the rate of change is decreasing because we are concave down. Okay, now take a second, revise your answers for the last one if you need to. Now that we've talked about how to work.
Yeah, so this one's definitely it's concave down. And like concave down. So the way you think about it is like the slope here.
This makes so much sense.
It's like it's when it's like that, it's just the slope being positive.
All right, so the graph of H
Like that would be like
is
versus like
positive.
that would be like 1.
The graph of H is decreasing. Everybody okay with that? Positive, decreasing. The rate of change,
Rate of change is the slope.
negative. Rate of change is slope. What's the slope of all this right here? The slope of this is negative because it's going down. The rate of change is decreasing because this is concave down. Okay? We're gonna have to do some more practice over that, but real quick, we gotta turn to the back of Pamela's current ski. Go to the back side of that.
So if this went up, it's like
We're not gonna get this done, but we'll finish it next time. Number 1, how fast is the tea cooling over the 10-minute interval? Show work and include units. What work do we have to show? The average rate of change is going to be H of 10 minus H of 0 divided by 10 minus 0. That is where your work begins. Does everybody understand why we're going 0 to 10? It says over the 10-minute interval. What's H of 10? 43. H of 0 is 66. negative 2.3. Alright, let's put a unit on it. What would the unit be? Negative 2.3 degrees Celsius per minute. Why is it negative? Because the temperature is cooling off. It's going down. Alright, one more. Estimate the rate at which the temperature of the tea is changing at 3.5. Explain your method. I don't know that there's necessarily a right and a wrong method. You've got to have some method. Alex, what do you think?
Could you like get the temperature or like find the rate of change at 3.4999 and like the one that we did first?
How would you do that though? Because we don't have an equation. Right, Julie? I think all we have is that chart. Scout?
I mean, since our slope is to, not my slope, slope intercept one.
Oh. Scout says we could write the equation of a line. Now, what points should we use if we're going to write the equation of a line and our goal is to do 3.5? What points maybe should we use? Maybe 2 and 5? That will be the closest. So write the equation of the line and then 3.5. Nice work, Scout. Great, sit down with Fran.
Father, Son, and Holy Spirit.